Great. So my slides are visible. Anybody confirms? My slides are visible, or Prathu?
Yes, sir.
Thank you so much. So let me just quickly recap what we have been discussing in last 3-4 classes. So first thing that we could do was we took an elliptic 2D conduction equation. Now you are slowly getting familiar to this. And how is it coming? It is coming from the heat flux equation. And then what we did, we did a separation of variable technique in order to identify the solutions like this. And for different types of lambda, which is a separation constant, we could identify 3 different sets of solutions. We enforce the boundary condition. We introduce the concept of theta, which is temperature difference. We simplified the boundary conditions here, enforced into the system, and then we obtain the constants. A typical set of evaluation of constant in the form of the Fourier sets has been given here. This is subject to your practice. Okay, this cannot be done in an online class. I cannot derive it. In a normal class, I would have derived it on the board, but even then it is meaningless. If you until or unless you do it yourself, you will not be able to really understand what's ongoing here. Okay. Now then we shifted towards what? A system which is the unsteady heat conduction. We thought we understood that del square T by del X square can give me the distribution of temperature across a geometry. Say suppose del square T by del X square will be true for a one-dimensional system. For a two-dimensional system, I will need to add X and Y. And for a three-dimensional system, I may need second-order derivatives of the X, Y, and Z. So if I have that sort of equation, okay, that will be able to tell me the spatial distribution of temperature across the geometry that I have chosen. This is a Cartesian coordinate. That's why I have taken a rectangular slab. If I take this in cylindrical coordinate, then I can describe a cylinder. If I take this in spherical coordinate, then I will be able to really calculate the same for a sphere. Now, what we understood that, say, in most of the situations, steady state temperature distribution is a very good, exercise to evaluate. But then, most of the engineering systems are dynamic in nature. So we need to know how exactly with time this thing is also changing. So we then considered this parabolic equation. Okay, then we enforced the temperature difference concept into this. And then we converted this equation to this, and we again rewrote the boundary condition like this, and enforced the separation of variable now in the parlance of what? Say this is the spatial derivative and this is the temporal derivative. Okay, and then if I combine these two solutions, I get a common solution like this, where I need to evaluate what? I need to evaluate lambda, I need to evaluate C2, and I need to evaluate C1. If I know these 3 constants, then I will be able to really calculate. So if I evaluate from the, so in this situation, I will have an initial condition, and I will have 2 boundary conditions, second order in space. That's why I require 2 boundary conditions. First order in time. That's why I require 1 initial condition. If I enforce this boundary condition, I end up getting a solution like this. Here we defined a parameter which is called the dimensionless temperature, which is the driving force divided by the initial driving force. This is the driving force at time t equal to t, and this is the driving force at time t equal to 0. And this doesn't have this as a unit of temperature. This has a unit of temperature, but this parameter doesn't have a unit of temperature. And then we see that this can be correlated to all the parameters that are known to me. It's alpha thermal diffusivity. Moment I fix the system, K by rho Cp, density, specific heat, thermal conductivity. I know already what is the material that I'm choosing. So suppose a steel slab is put into water. So I know all the parameters. I know the dimension. Okay. Now the time that I'm measuring, I also know. So in that process, you know that the right-hand side is entirely known. This is a series. So I just have to keep adding all these things in order to get an analytical solution in terms of for the temperature, for the temperature difference, and for the dimensionless temperature. Okay, so you can really see that this is possible analytically, And then what we did, we defined a system which is called a lump system. Okay, where we assume that, okay, this temperature change can be because of conduction, but this temperature change can also because of this temperature. Kindly mute. Okay. Yeah, thank you. So this Harindra, kindly mute. Thank you so much. Yeah. So we can also equate, like previously what we were doing, we were equating the conduction to the temperature change, temporal temperature change. We can also correlate this with the convection that is happening around this with the change. And in that situation, we could come up with another solution. This is the dimensionless temperature at time t equal to t. So this is my equation. If I integrate, I'll end up getting something like this. If I enforce this initial condition, this is a first order in time only. There is no spatial derivative here. I'll end up getting a solution like this. Now from here, we came up with a dimensionless number, which is called the BO number or the Biot number. Okay. Now here we realized a concept that this rho CV is the capacity system to hold the heat, whereas 1 by HA is the resistance for the convective heat transfer, right? So what we did, we went for what? We went for the analysis of this parameter, which has a unit of time inverse, and we analyzed this parameter and we found out that this is nothing but the combination of the reciprocal of the resistance to thermal resistance to the thermal capacitance. What is thermal resistance? Is 1 by HA. What is thermal capacitance? Is rho CV. And one can express in a very similar to like in an electrical circuit. One can really express this as a kind of, it's a combination of a parallel combination of a capacitor and a resistor, which is applied through a voltage through this. Okay. And from there we understood the concept that of the time constant, which is coming out to be C rho V. So this is the amount of heat storage, and this is the amount of heat dissipation through convection. Okay, so this amount of heat storage and heat dissipation through convection. Okay, so capacitance and resistance concepts were clear. And then from there we defined a parameter called BO number, which is H V by A by K. Now K is the thermal conductivity of the metal, of the solid. H is the heat transfer coefficient of the fluid medium that is surrounding it. And V by A is the geometrical parameter that is associated with the solid. So suppose if you have a heat exchanger, V by A is associated with pi. Suppose you have a steel ball that is immersed in water, V by A is associated with the steel ball. K is associated with the steel ball. But H is associated with the surrounding fluid, which is withdrawing the heat through convection. Okay, so what is the ratio of these two? This ratio actually talks about K is the conduction, the capacity of the conduction, how fast the material can conduct. Whereas H is a measure of what? H is a measure of like how fast the fluid is convecting them. So the ratio actually tells that in this situation, which resistance is more, whether the convective resistance is more or the conductive resistance is more. So suppose if you put a metal ball into water, of course you will find the convective resistance will be more than the conductive resistance. And that's why this value will be, you can expect this value to be, see conduction resistance will be reciprocal of that. Convective resistance will be reciprocal of that. So in that process, you will find that this value will be 0.1. Okay, there is a little bit counterintuitive here. Okay, that you have to understand that H is a measure of convection. Resistance is 1 by H. K is a measure of conduction. Resistance is 1 by K. Now, if you take the ratio of these two, you will find out when the conduction resistance is more. When the conduction resistance is more, that means it's 1 by K. When the convective resistance is more, that means it is 1 by H. Okay, so essentially when it is, that means when this value is small, that means if you have a metal, in the metal there will be no such temperature difference, whatever you are heating up, that is getting convected to the boundary, that is getting conducted to the boundary immediately. There's no time lag associated with that. But from the boundary, the temperature is slowly dissipating out. And for that sort of system, you have this BO number to be very small. We did some of the problems. Whereas if the conduction is very slow, then you will have another situation where the BO number is high. And this V by A, this parameter is called as S, which is the characteristic dimension of the solid. Volume by area, we have defined surface to volume ratio or the volume by area. This parameter is defined as a characteristic length scale. For a semi-infinite pipe, it will be the diameter. For a semi-infinite plate, it will be the thickness or the width. Okay. For a sphere, it will be the radius. So that's the way you define the characteristic length scale. Fantastic. Now, once that has happened, then you post two different situations. We are just taking one by one just to study how these things are happening. One situation is conduction, is transient, and the other situation is conduction is transient. Conduction is transient, but you have a Dirichlet condition here is T0. This wall is facing a Dirichlet T0 condition, okay, isothermal wall, and then I'm going for an adiabatic wall or a kind of heat flux wall. Adiabatic means Q will be 0. So that's a heat flux condition, or I can put a kind of Q0 equal to minus K. So I can define on the wall two different types of boundary conditions. One is I can fix the temperature, okay, or I can fix the heat flux. Okay, I can fix for an adiabatic wall, heat flux will be 0. That is not an isothermal condition. That is not a temperature condition. What does it mean? That there is no temperature gradient across. That means if you put an insulator, in that situation only that del T by del X becomes 0. So you don't allow any heat to flow across that. The gradient is 0. Whereas when you put an isothermal condition, you put a temperature condition. Now, if you look at this particular system, and if you enforce a temperature Dirichlet condition at this place, okay, so at x0, 0 is the initial condition. This is Ti, and at 0, that means at this place 0 and tau, it is T0. That's the way if you define, you get a solution like this. From there, if you calculate the heat flux, you get a solution like that. Okay, so you can really calculate Q0 using this equation. Okay. On the other hand, if you enforce the heat flux boundary condition, the solution changes a little bit. Okay, and from there you again obtain an equation like this. Okay, now if you plot them, if you fit them, we define that you can really make the length scale also dimensionless, and you can make the temperature also dimensionless. So we showed that there are two ways of making the temperature dimensionless. This one we made with respect to the temperature difference. The dimensionless parameter of temperature has been defined with respect to the temperature difference. X is defined with respect to the root over of alpha tau. Alpha is the thermal diffusivity, unit is meter square per second. If you multiply with time, then what happens? Meter square, and then root over of means meter. So this is dimensionless. Okay, and this becomes a dimensionless temperature parameter. Similarly, you can see that this is the temperature can be expressed in terms of flux like this, and then if you divide by the flux, so this becomes another dimensionless parameter. This is in terms of flux, and this is I just if I just square this parameter, so I'll end up getting this parameter that can also become a dimensionless length parameter. Meter square per second. Second, that means alpha tau is meter square cancels out, and that gives me a dimensionless length parameter. And then I can really draw these functions to see how exactly the temperature profile is changing with respect to space and with respect to time. So in a single plot, you have the entire piece of information starting from density, starting from thermal diffusivity, starting from capacity, starting from driving force, starting from initial heat flux, starting from what is the total length, at which length, what is the temperature, what is the thermal diffusivity, and at what time, what is the temperature. So this plot is a self-explanatory plot that, with time, how, in which place, what will be the temperature. You looking at this plot, you can just quickly identify. That's why these plots are so important. So you are starting with a transport equation in Reynolds transport theorem. You are reducing it to a manageable form. You know that those equations are big. Okay, when I ended up writing the entire transport equation for energy balance, it was in terms of energy. Then we did some assumption. It came in terms of internal energy. Then we changed it in terms of enthalpy, and then from there we assume we enforce Fourier's law in order to get the transport equation for in terms of transport equation for energy in terms of temperature. Now that's a 3D equation. Okay, it's a 3D hyperbolic, parabolic. All signatures were there: hyperbolic, parabolic, and elliptic. So what we did, so we smartly just took the conduction term to study the steady state part. We took the transient term to study the parabolic part, and in that manner, we reduce these equations in the manageable forms that are required for the systems that I'm choosing. And then we did assume separation of variables and enforce very smartly the boundary conditions to get simple analytical solutions like this, okay, which can really describe how the temperature, suppose this is a slab, how the temperature is changing across the space in terms of space and with time. How the temperature is changing in space and time. This plot actually tells, in a single plot, I'm able to really get all the information that are required. Now, if I can change this boundary condition into a convection boundary condition, if I do that, the same error function equation changes a little bit. Okay. Now this can also be plotted like this. So you see that again another way we have defined the x by, I have just taken the square root of the previous plot. And here what we divided, we defined theta by 1 minus theta by theta. So different ways people have plotted it. Okay. And this is not in terms of time, but this is in terms of what? This is in terms of h alpha by tau to the power half. So this is in the form of BO number you have plotted in order to make sure that again you have all the information associated with this, when you have a convection boundary condition. Okay. So here, we define what? We define Q to be this. Now what we said that this Q is nothing but a little bit, this Q is nothing but HA T infinity minus T at x equal to 0, which is equal to minus K dt by dx. Slight change in that, is going to change your solution like this. And these are all very seminal contributions while, the subject heat transfer progressed. And from there, these analytical solutions are not now readily available. So for a slab, now later on you will see for a cylinder, for a sphere, all these solutions are available, and these solutions you can make use in order to do an engineering calculation. That's a, suppose if I take a cylindrical object, how is the temperature profile that is going to change with respect to space as well as with respect to time. Okay, so we will see some of the examples. So you can see that this is a slab, this is a cylinder, this is a sphere. Okay, this is called an infinite plate thickness. This is an infinite cylinder with a radius of r0. This is a sphere with a radius of r0. And you may see a collection of plots now, which are typically called the Heisler charts. Okay, which actually is plotted in terms of two-dimensionless number. Okay, one dimensionless number is the BO number, and the other dimensionless number is the Fourier number. Okay, how does this appear? So we are discussing what is BO number. BO number is HS by K. So BO number means that the internal conduction resistance. You have a solid object. There is an internal conduction resistance. Okay, the ratio of internal conduction resistance, since K is at the denominator at the top, it will come the internal conduction resistance, because we know that resistance is reciprocal of conductivity to the surface conduction resistance, which since this H is at the top, I can say that surface convection resistance is at the bottom. So internal conduction resistance divided by surface conduction resistance, BO number is a measure of that. Now, if the internal conduction is very small, resistance is very small, that means it is metal. And if the outside conduction is very high, internal conduction is very high, then I can say that resistance is very small. That means it is metal, and BO number is very small. Okay, so you can see that these are typical situations where the BO number is small. This is the intermediate. This is at very high. So this is the domain where you can expect that the material to be an insulator. This is the domain, you can expect that material to be a metal. Whereas we defined another parameter based on the time constant. Alpha is the thermal diffusivity, meter square per second. Tau is the time, alpha tau is meter square, divided by a square. A square is my, S is my V by A, which is the characteristic length, and the square of that. That's the way we were plotting here, right? In all these, we were plotting with respect to this. So now this you formalize in terms of a dimensionless number, which is called the Fourier number, where this is the diffusivity and this is the typical length scale. So Fourier number compares a characteristic body dimension. Okay, what is a characteristic body dimension? For a semi-infinite slab, this should be L or 12. For a semi-infinite cylinder, this should be R. For a sphere, this should be R. Okay, so there is a characteristic body dimension with an approximate temperature wave penetration depth. Alpha tau gives me, alpha is the thermal diffusivity, meter square per second. If I multiply this with time, it gives me how much the temperature wave has penetrated into. Okay, at time t equal to t. It's a length scale. This meter square is actually root over of this alpha tau gives me how much meter that wave has penetrated. So how much wave has penetrated against the dimension. So this is defined as the Fourier number. Okay, and importantly, if you multiply Biot number and Fourier number, you end up getting HA by rho CV into tau, which was the case where, which is the numerator of this, HA by rho CV tau. Essentially, HA by rho CV tau, rho CV into tau means what? 1 by the thermal resistance into thermal capacitance into the time scale. So basically, the characteristic time scale that I am taking, okay, the second inverse is of that. If I combine the whole parameter, this is coming out to be my BO number and Fourier numbers multiplication. Okay, and this is very, very important. So what I do, I plot against any one of them, and then I vary. Say suppose I plot theta by theta 0 by theta I with respect to Fourier number for different BO number. It is also possible to plot theta 0 by theta I in terms of BO number for all Fourier number. That actually gives me the total picture of what? Total picture of what? How exactly temperature is propagating into the system. And these particular charts are called Heisler charts. See, suppose in a problem, what I will do, I will give dimensions of the metal, and I will give you the density and capacity and all these things. And I will tell you that, say suppose after 20 seconds, what will be the temperature? Looking at this plot, you can really identify the temperature, you can really identify the heat flux, the temperature at the boundaries, temperature at any space that is there inside. That is the beauty of the chart. Okay, similarly, you can see that. So if I just focus on this part, so you can see that this is the low Fourier number situation. Here you can see that these are all log plots, right? There are log plot. This is also log. This is also log. So 1 to 10. Okay, 10 to 100, and then 100 to 700. So you can see that. Say suppose in 1 to 0.1 to 0.1 to 10, you may see them to be linear. Okay. Say for a infinite plate thickness temperature as a function and temperature as a function of center temperature in an infinite plate. So you can see that if I plot, this is 1 by BO number. This is against Fourier number. This is against 1 by BO number. So you may get a plot like this. Now X by L, again you can see these are all different Fourier numbers. You can plot in terms of different Fourier numbers, right? Now again 1 by K, this is for a cylinder. This is for a sphere. So these type of plots are all available with you, which actually gives you what? Which actually gives you the temperature distribution in a geometry with respect to time for a given system, and you can make use of that charts for calculation. Why these things were developed previously? Because computer revolution did not take place. So this is about, we are talking about 1920, 1950, 1970, when there was no computer. And people had to do all the calculations analytical, and you have to understand that all this heat transfer business started after the industrial revolution. Okay, so post 1750 and all, the French Revolution, after that the Industrial Revolution, okay, where the modern science, modern engineering took off. I suggest all of you to look at the history of chemical engineering. You will find that it's one of the very new subjects. I mean, the most contemporary three engineerings are electronics, computer science, and chemical. Chemical, it started with chemical, then came electronics, and then came computer. And it has a logical chronology. Chemicals were required to synthesize the materials. When we went for large scale materials, we did realize the electronic properties. Now, moment you made the PCBs and all with electronics, the computer revolution took place. So these are the three latest, engineering. Civil engineering were there for long. Okay, mechanical engineering were there for long, right? But then these are the three main engineering, modern engineering subjects which has emerged in only last 100 years. Okay, and heat transfer is one very important component of mechanical, chemical, electronics, okay, computer science. In all the cases, heat transfer has played a huge role, and the development is, as you see, civil engineering was needed from the beginning of the civilization, right? Now you needed other different types of engineering, like textile engineering, okay, like paper and pulp engineering. These were there, like writing, inks, and all these things. These were there, but they were never went for a large scale production. Now, industrial revolution led to the emergence of mechanical sciences and mechanical engineering in a huge way. Invention of steam engine, invention of automobiles, invention of rocket. Okay, all these things that took place from 1750 to 1950. And in those situations, moment you are having these, internal combustion engines, or moment you have the ships, moment you have these different types of automobiles, the calculation of energy conversion efficiency and all, and becomes very, very important, rather like inevitable. And simultaneously you see the developments of the subjects like thermodynamics, like heat transfer, like fluid mechanics. They are slowly being developed with the mechanical sciences, and slowly they became the part of chemical engineering. Why? Because internal combustion engine means it's a chemical engineering. Okay, reactor means it's any reactor, any nuclear reactor inside a rocket. Any type of reactor means it's a reaction engineering, mass transfer associated with the heat transfer. So these were the charts that were used extensively, prepared up to 1970. These were the charts that are prepared, used extensively for the calculation of what? For the calculation of temperature, for the calculation of the heat fluxes, with respect to time, with respect to these dimensionless numbers, for making different types of calculations, design calculations that people were doing. Okay. Now, of course, they did not have any other choice to put up the analytical models. So you saw that we went for a one-dimensional system. Then now, how do I make it more complicated? Why am I making more complicated? Because now I want to know. Once I am satisfied with a slit, now I want to go for a slab. And for a slab, you can see that this is again I am using a separation of variable technique. But you know that these analytical solutions will have a limitation. Why? Because from the beginning itself, I am just making them linearly independent in each dimension. Now that is not the case always. Okay, so I take the equation, I separate the variables. Again, I'm using the same trick. You can see that first you decouple them, and then you take this is to be x, this is to be z. So you get two parabolic equations. You enforce a solution, and then you get a linear combination of the two solutions, right? So this is the way people were solving different types of geometries, like a kind of plate, like a slab, like a cylinder. This was up to 1980s and 1990s, before the CFD revolution took place, which we will discuss very briefly today as we progress. Okay. Okay. Now, just to finish the entire thing, while calculating these things, and from where exactly this CFD thing that emerged, people started really after doing these analytical calculations, which we have been doing for last 5-6 classes, starting from developing the transport equations, simplifying them, in terms of geometry, converting them, and then looking for simplified analytical solution in the form of separation of variable. After doing all these things, people came up with this particular concept, which actually led to the led to the invention of the computational fluid dynamics. Okay, what is this? So you can see that this is my Fourier's law. How is it? Q is my heat flux. Okay. Now delta T is my what? Delta T is my change of temperature, right? And this is to be divided by delta X, which is typically M by N. I will come to that. What is M by N? So Q is equal to K into delta T by delta X. This I can write in an algebraic form. See, I have an equation which is Q equal to minus K into dt by dx. It's a differential form. This differential form I can write in terms of a shape factor, okay, in the form of an algebraic equation. So you can see that this is nothing but an algebraic equation. I have converted the differential equation into an algebraic equation. Now, what is this situation? I say that, say, suppose this is a kind of like hollow plate. Okay, so this is my outer boundary, this is my inner boundary. Here it is air, here it is air. I was working with a very simple system like a plate, and I can enforce x equal to 0, x equal to L, y equal to 0, y equal to L. I can apply a boundary condition very easily. But if I make a hole in the plate like this, a rectangular hole, which is a very simple hole, typically the hole is a circular one, then what happens? Then again, now I have to enforce so many different types of mathematical equations in the form of boundary condition in order to get the temperature profile for this. So what people started doing, and these type of geometries are very common in engineering systems, right? So suppose you have so you can imagine that if this is a type of shell, rectangular shell. If I just make it circular, then this becomes a cylindrical shell. Cylindrical shell is a very common geometry in a heat exchanger. Okay, so people started thinking that how exactly we manage analytical solutions here. So what did they do? They went on like solving this equation using separation of variable, and they introduced a concept called shape factor. What is that? They say that N is the number of temperature increments between inner and outer surfaces. Say suppose this is T0 and you have divided into different, say 1, 2, 3, 4 boxes. So N, say this is T0 to say Ti plus 1, Ti plus 2, Ti plus 3, Ti plus 3 is, say suppose this is Tu, which is outside. Okay, so N is the number of increments between inner and outer surfaces, and M is the number of heat flow length. So this is one heat flow length, this is one heat flow length. So what did they do? They converted this particular plate into a number of simpler plates of 2 dimensions, and then they kept adding that in the entire geometry in order to get the overall. Right? So essentially they were using they converted this differential equation into an algebraic equation, okay, and then they kept adding into the entire system in order to calculate the total heat flux. So in that situation, what did they do? So they defined S to be what? S to be a factor which is M by N, which is called the conduction shape factor. Okay, and then how do you define this? You define S wall as A by L. Okay, S edge as 0.5D. So it has a dimension of, so you know that Q by A is equal to Ka dt by dx. So A by dx, delta T by delta X. So what is A? A is denominator, you have this A, that is coming as S. So A by L is your S wall. And for an edge, say edge is like this. Okay, this is 0.54D. Corner is 0.54 L. So from the geometrical parameter, this is a corner, this is an edge. Okay, so from all this, what happened? Like you are able to really get different types of, for cylinders, okay, for isothermal sphere. So different types of conditions were created to create a huge database of different types of engineering geometries which are prevalent, and you can see that S was calculated. Now moment S is there, what you do for overall, you calculate the heat flux like this. This was going on for a while for different types of systems. I have given many examples like hollow cylinder, hollow sphere, okay, isothermal, okay, insulated. Different types of equations, analytical equations were created. And remember, they actually were giving very good results. And all the calculations that were done using these shape factor equations, and we ended up getting real good solutions until people realized, and this was a concept which was introduced by Euler, 1800, 1700, 1800, he was doing these calculations about 200, 250 years back. He was doing these calculations. He said that the easiest way to really tackle most of the complicated partial differential systems is by solving them numerically. Okay, so I just go through this part a little bit more detail with all of you. This is very, very interesting because this is the starting point of the modern engineering, which is the soft engineering. So what he proposed that, say, I can really think about any particular point. If I'm really focusing, I can really focus on a particular place. Okay, this is the focal point of mine, where I can say that this point is M. I can define this particular point as what? Mn. Okay. Now what I can do, I exactly need to know what is the temperature at say suppose point which is M, and say suppose point which is M. What is M? Say I define that there are m number of points in this direction, which is my x coordinate, and I define, say suppose in the y direction I have n number of points. Okay. Now say if this is Mn, so what will happen to this one? This will become my M plus 1 and N, because it is at the nth level, and this will become my M minus 1 and N. So I am able to define this point, I am able to define this point. Okay. Now I can also define two other points, okay, which are the neighbors. This is what? Now this I have graduated to N plus 1. And this remains to my M, because I did not change my X. And this becomes N minus 1 and again remains and remains N. So if I can really calculate this one from these four, and if I can do for all the points, okay, in an M by N array, I am really able to get the heat transfer that is calculated here. This is the starting point of the whole system. That, so suppose what is the issue? The issue here is that, let me just put another slide here, because this I may need later on. What is the issue here? Issue here is that I have to calculate different types of. I have to calculate, say suppose I have a geometry like this, right? And say suppose I need to solve an equation here, which is, say suppose del square t by del x square, okay, plus del square t by del y square equal to 0. Say I have to solve this equation in this space and time. So this is my x coordinate, say this is my y coordinate, and this is 0, this is my y, and says this is my x. This is my x, and I need to know the temperature profile here. And I know what are the temperatures. Say suppose the temperature is T0 here, which is one of the boundaries. Temperature is T0 here. What are one of the temperature is, say suppose T1, and say suppose this is also in T1. So I just change the boundary condition like this. Now how do I do that? So what Euler suggested, that you first convert this equation. This is a differential equation. You are finding it difficult to solve the differential equation. Okay, you have got two second order equations, second order in x and second order in y, and you have got 4 boundary conditions. So you have satisfied everything associated with the boundary condition and all. What you do, you convert this system into a set of algebraic equations. Okay, how do you do that? If you can convert that, if you can convert this into a set of algebraic equations which has got n number of equations and n number of unknowns, including the boundary conditions, then you will be able to solve it. Okay. So what is the proposition that he has given? He has given that first you assume two things. What is number one? The function, that variation of the temperature across this is a continuous function. It is not a discontinuous function. It is a continuous function. This is the first assumption. Okay. And second assumption is that if you can divide this into very, very small elements, the accuracy of this partial differential equation and the algebraic equation is remains same. So I have divided this into, say, suppose 4 boxes. What you expect? You just divide this part. I just do it here. You just divide this box into n number of small boxes like this. Okay, as many as possible. Okay, in delta x and delta y, and you make sure that this is a kind of system where you make sure that there are as many boxes as possible. More are the boxes and more is the accurate. So first is in the discrete space, algebraic equation map 1-to-1 to the partial differential equation. And second is what? The temperature which is changing across the space and time remains continuous. These are the two assumptions he made, and he could come up with what is that? If I make these two assumptions, what is the advantage that I get? If I have a function, which is say, suppose I'm just writing in terms of age, if x of x plus age, what I do, this I am learning from say class 8 and 9, that what is the equation for derivative? If I do a Taylor series expansion, this will remain to be say fx plus h f dot x plus a square by 2 factorial h f double dot x, okay, plus h cube by 3 factorial f triple dot x, okay, and so on. Right? Now, if I write f of x minus h, how will it look like? Same, but alternate. I will have f of x minus of h. Alternate, I will have minus. Right? What is this series called? This series is called the Taylor series. So you can really convert. So fx plus h, a little bit of increment, say from x to a little bit of increment. This is this h is what? This h is here, this distance. This h is here, this distance. This particular distance which I am talking about h. Okay, here I am talking about this is to be, sorry, this particular thing to be, I'm talking about this particular thing to be h. Okay, the distance for a particular cell. Okay, so if this h is very small, what is your equation for derivative? How do you obtain derivative? So suppose you say that when h tends to 0, you write that when h tends to 0, limit h tends to 0. What do you say that? You say that f dot x is what? F dot x you can write as fx plus h. Okay, minus fx divided by h. When h tends to 0, when this h is very small, when you have a differential element, what you are doing, you are converting this differential equation in the form of an algebraic equation. Okay, so exactly this is what he has proposed, that you convert all your equations into you convert all your equations into what? You convert all your equations into partial differential equations into the linear algebraic equations. Okay, and then what you do, you solve those linear algebraic equations in order to get a complete solution. This is the modern interpretation of, rather than going analytical, rather than simplifying and going analytical, because we know that in the full swing, if I take the full swing equation, until today you do not have an analytical solution for this full heat transfer equation. And if you do that, that's a Fields medal. That's a Nobel Prize in physics. Okay, if you can come up with a why physics, because it's an applied math. Okay, so you know that there is no Nobel Prize in maths, right? And you also know the reason. See, Alfred Nobel's wife was a mathematician. A wife actually fled with a mathematician. She left Alfred Nobel and she left with one mathematician. That's why when Nobel Prize was drafted, Alfred Nobel said that mathematicians will not get the Nobel Prize. Okay, so you have medicine, you have physics, you have chemistry, okay, you have economics, different types of Nobel Prizes are there, but you have literature, you have peace, you don't have Nobel Prize for mathematics. So mathematics, what is the highest prize? It is Fields medal. So if you can solve the full heat transfer equation analytically, which we were attempting up to this point, it's a Nobel Prize or it's a Fields medal. But then if you cannot do that, this is the way it has been solved, which is the numerical way of solving the equation. So you convert the partial differential equations into what? Into the algebraic equation. How do I do that? Let me just show you. I just remove this part. Now this is this derivative part you all know. I have just written this thing. I'll just make sure that. I'll just make sure that, say suppose in this situation I do an addition. I will do two things. One is I do an addition, and then what I do, I will do a subtraction. Correct? Now, if I do an addition, what will happen? So these two will come out to be what? These two will come out to be, say, suppose this is coming out to be f, x plus h, plus f, x minus h. This will become equal to what? 2 into fx. Okay. Then you may see that these two will go out because I'm adding. Then it will become like h square by 2 factorial, which means 2 into what? This will again, add up. So 2 will go. So h square into, sorry. H square into f double dot x. Okay. And then what will happen? Then again, this will go out. And then what term will remain? Then I will have h to the power 4 by 4 factorial into what? F to the power 2 into, this will have 2 into x. And then I have many terms. So many terms. This if I do addition. So from here, you can really understand that now f double dot x can be written as what? So if from here, if I simplify, I can write f double dot x as fx plus h minus 2fx, okay, plus fx minus h divided by what? F double dot had h square. This is h square. And then if I divide this one, this will be what? This will be a term. I just write this in the form of order of h square. Okay. So you can see that the definition of second order, right? This is the second order derivative. This means d square f by dx square, del square f by del x square, which I can convert into fx plus h minus 2fx plus fx minus h by h square. Okay, what is x plus h? This is my x plus h. What is x minus h? This is my x minus h. And what is my fx? This is my fx. So around this point, I am able to evaluate the partial differential of second order. Now, this is a Taylor series. Okay. Now, this is an infinite series. There will be infinite number of terms. But if I say that if h is tending to 0, h is becoming very, very small, I can truncate this. So here what I did, I truncated the terms from h4 onwards. So I have committed an error which is called the truncation error. So I'm saying that I'm going to ignore the terms that are there, that is more than h to the power 4 and all. And in the form, the accuracy that I will obtain. So what is the truncation error? Truncation error is associated with this part. This is my truncation error. Since I have ignored all the terms bigger than this, I have truncated the series. I am committing an error which is called the truncated error. And what is this term? This is my the level of accuracy. So since it is h square accurate, this is called a second order accurate. Okay, see, when I did fx plus h minus fx divided by h is equal to f dot x, when I defined the derivative previously, what was my error? Order of error, you may see again, when I divided by h, the order of error was h. Okay, so it was a first order accurate. So if I write fx plus h in terms of what? Say in this equation, if I write fx plus h, say suppose f dot x is equal to fx plus h minus fx divided by h. What is the term here remaining? You will see that h by 2 factorial. Okay, then you will have what is that? H by 2 factorial into f double dash x. So this particular term will be what? This particular term will be. So if I truncate here, as I was telling that if I truncate here the entire thing, so this will be a first order accurate f dot x. Okay. Now how do I get the second order accurate f dot x? You see here. Now I was doing addition here. Now let us do a subtraction. So let me do a subtraction. I just subtract it. What will happen? I will get f x plus h minus f x minus h. So what happens? Fx is gone now. I have equal to 2h into f dot x. Am I correct? So this minus, since I am doing a minus operation, this becomes plus 2h into f dot x. Since this is minus, this one goes away. And then I will have what? 2h cubed by 3 factorial. Okay. 2h cubed by 3 factorial into what? 2h cubed by 3 factorial into, because this minus will become plus, this will become minus. So f, I will have triple dot x. Correct? Now you see that fx plus x, I just put it here, fx plus h minus fx minus h. So f dot x becomes what? If I divide this by 2h, entire thing by 2h, and if I take this one, if I want to evaluate this one, so what is the truncation error? H divide. So this becomes a second order. So you can write a second order accurate f dot x is what? You can write a second order accurate f dot x as f dot x is equal to what? F of x plus h minus f of x minus h divided by what? Divided by 2h, and the term that is remaining here, if I dividing by 2h, that is of the order of what? This is of the order of the term that is remaining, that is of the order of what? This is of the order of h square. So this is a derivative which is a first order accurate. If I take straight away from the Taylor series, if I do a little bit of mathematical jugglery, I can really get a second order accurate. This is called a forward difference. This is called a central difference for first order, and this is called the center difference for a second order. Okay, this is second order accurate central difference. This is why central difference, because you can see that I am doing this fx with respect to what? When I am doing this with respect to these two, it becomes a center difference. When I am doing between these two, this becomes a forward difference, m plus 1 to m. When I am doing between these two, this becomes a backward difference. Say suppose this one also I can use for the evaluation of the first order, right? So what will be the first order will come there? If x minus h minus fx divided by h, which will become my f dot x. So that is called a kind of backward difference. So this particular thing is called a stencil. What is the stencil? For an m, say I have a full system which I have divided into mx components and ny components, and I make an m by n array. In the m by n array, I find a particular point m and n. When I am looping over n, I find a point m and n. And at m and n, what I do, I evaluate all the derivatives associated with this. How do I evaluate? I first, put the stencil, and around that for the derivatives, I have derived f double dot and f dot for you. So what I do, I put these, this f double dot x is what? Partial differential. This is the corresponding linear equation. What is f dot? This is the partial differential equation. This is the first order accurate algebraic equation. This is the partial differential equation. This is the first order accurate, second order accurate central differential equation. So what I do now, let me go back to my slide. What I do, I say that for a particular point m and n, okay, you can see that what I did that tm plus 1n minus tmn divided by delta x. I just convert this partial differential equation into an algebraic equation. I just convert this partial differential equation into an algebraic equation. So you see that we have just now derived delta square by delta x square. What I do, tm plus 1n, okay, minus 2tm1. So this is the equation that we have derived here. What is that? X plus h minus 2fx plus 2fx minus h, right? So you can see that this equation is coming here, that this is x plus h, this is x minus h minus 2fx divided by delta x square, that is h square, okay? And then the same happens in the y. So del square t by del x square, del square t by del y square, okay? I convert these two partial differential equations into what? Into a set of what? This is the linear algebraic equation. And then what I do for this equation, del square t equal to 0. So you can see that straight away it comes out to be an algebraic equation like this. And this is true for all the m and n, including the boundary points. So suppose this is a total system. When I am going for this is 1 m and n, 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 okay? So I can really, and then what I assume delta x to be delta y, so that I convert this to a set of, I take the entire plate and I can convert it to very small finite length boxes, squares, as many as possible. If I do that, I end up getting an analytical delta, and I put delta x equal to delta y to get an analytical equation like this. Okay. Now this analytical equation is what? This analytical equation, you can write as what you are doing. And for each node, you have this T is the temperature and A is the coefficient. You have a temperature and you have a coefficient associated with that. See, there is 4, there is 1, there is this minus 4, this is 1, this is 1, this is 1. So for each point, you have a coefficient. So you can write in terms of a linear equation, set of linear equation. This is an m by n array. Okay, so m in the x direction and n in the y direction. Okay, so this is an equation. This is the right hand side. This is the left hand side. Temperatures are there and their coefficients are there, right? So you can see that the entire system can be written in the form of a set of linear equations where you have n number of t1 to n. You have n number of unknowns, t1 to tn. Okay, and you have got n number of equations. Simple Gauss elimination you can apply here. Okay, so this can be written as what? This A is the coefficient matrix, C is the constant matrix in the right hand side, and T is the variable matrix. So it can be written in a very simple manner that A matrix to T matrix is C matrix. And what is the solution? T is A inverse of C. Now, if you evaluate A inverse, if you multiply by C, T1 to Tn. So you exactly know what is the solution across the space. Okay, so this is the onset point of the computational fluid dynamics, through which right now most of the calculations are made. So I stop here. One slide is remaining. I will do a little bit more discussion. Maybe next class, 15 more minutes, we'll discuss about this before we move on to the other subjects. Any question you have? Any question? Anup, you have a question? Yeah, so I'm going to send you, if you don't have a question, I'm going to send you the details of the schedule. So we are especially planning Saturday morning, Saturday evening, and Sunday morning and Sunday evening. Okay, so we'll divide into, most probably we'll be able to finish by Sunday morning. I will see, like, how much time it takes. Typically 7 to 10 minutes for a student. And as I discussed in the previous class, that the lectures, all the lectures up to 2nd of October and all the tutorials up to 2nd of October will be your syllabus of the quiz. Okay, I will put up one slide or one doc file, and you have to explain me certain things that I'm going to ask, and based on that, it will be random, and you will be evaluated based on your answers. And the entire thing will be recorded. Okay. Achha, the other thing is that there is no tutorial this Friday, so you make preparation. Tutorial solutions will be circulated by Friday morning to you. Before that, you have to submit your tutorials. After that, you will not be evaluated. And lectures I have already shared with the TA. So you have all the lectures, latest lectures up to lecture 8. So thank you and all the best.